so here was our space station. We decided that if we wanted to build in artificial gravity, we had to spin the space station, right?
Yeah.
And that produced what we might call centrifugal force, but it's a fictitious force. It doesn't really exist, right? Remember what we said was that really what's going on is just that the floor of the space station is providing a normal force that is pushing you out of your straight line motion. And so you feel a force with the floor. You feel that normal force, which feels like gravity then, right? Okay. So anytime we want to have an object that is spinning in uniform circular motion, then in order to keep it traveling in a circle, we have to be able to provide some kind of centripetal force, some kind of force that's directed, right? Does that make sense? Okay, and let's talk a little bit more about that. So what does that word even mean? Well, centripetal means center seeking. So a centripetal force is always is a force that always points towards the center of the circular motion. So in this case, the force that's acting on this person, and this works out perfect because it feels like gravity. There's a force acting in that direction towards the center of the circle that is changing their motion from being straight into a circle, right? Okay. So we want to know, what we'd like to do today then is we'd like to figure out, okay, so what is, can we come up with some kind of an equation that's gonna calculate this centripetal acceleration, right? Because really all the centripetal force is just centripetal acceleration times the mass of the person, right? He's being accelerated because, think back to what the definition of acceleration is. Acceleration is equal to change in v over change in t, right? Well, is the speed of this person changing? They're traveling around the outside of this, like when you're on a merry-go-round, you're traveling around the outside at constant speed, right? Mm-hmm. If you were to look down and watch how fast the gravel's whizzing by underneath, you'd find that it's the same speed the whole time. So the speed's not changing, but your direction is always changing, right? So for example, from this point right here to just a little bit later, when this person is standing over here, speed's going to be the same, but the velocity vector has changed directions, right? Mm-hmm. Velocity is a vector quantity, so that is an acceleration, right? Even though the speed stayed the same, the velocity direction changed, and so therefore there is an acceleration. So what we want to do then is we now want to see if we can come up with that equation, and that's what we started doing yesterday. Broken problems.
Are they actually thinking about having something like that, like a space station?
I mean, yeah, that is definitely. At some point, there will be something probably very much like what we're talking about, because that's the only way to simulate gravity is just to spin something, right? So yeah. Why is this thing? That looks a little weird, doesn't it?
You can't
feel like mountains.
Oh, you're gonna miss mountains.
Feeling them too.
Yeah. You guys go travel. Just like stuff in space. I just like to feel. I want to make sure they feel important too.
They feel sunshine. Look at the mountains.
Okay, so here's what we came up with yesterday, right?
Yeah.
Okay, so what we want to do then is we want to see. Here's this object, and we said it was just like I think it was a rock on a string or something, right? So here's the string. Here it is at time 0, and here it is sometime later, right? Okay, as you know, if the time is a lot different, then it's clear down here. But notice that the magnitude of these vectors are the same. It's just that their orientations have changed, right? Directions have changed. So what we want to do then is we want to see if we can come up with a relationship. So this is our initial position, that's our final position. Here's our initial velocity, there's our final velocity. So I'm going to do something tricky here. Let's take these vectors and I'm just going to copy them over here. Okay, now remember vectors are things that we can translate around, but we just can't change the direction or the magnitude, right? But we can translate vectors around to add them up tip to tail, for example. We do it all the time, right? So, see if I can remember how to do this. I want to take this guy and let's translate that guy a distance of, I don't know how far. Let's just say 10. Sounds good to me. 10 at an angle of 0. Yeah, that's going to be about right. So there it is. Okay. Now let's translate this one.
Wait, why is there a dot? Did you accidentally take a dot?
I don't know what that dot is. Oh, it's okay. So it translated somehow. I don't know why it did that, but not sure. I'll make him disappear though. We don't need him. Okay, so now I'm going to mark a vector on here. So I'm going to go from there. Oops. Oh, what happened to my points?
You took them all off.
Gotta go back. I'm going to undo. I got to undo a few things. Okay, so what I really needed to do is I needed to grab this whole thing. Not just the segment. I need the endpoints also. Those are important. Now let's try that again. Translate. What do we say? 10 at 0. So there it is. Okay. So now we want to move this guy along that vector. We're going to translate it along that vector. So I'm going to mark the vector, and then I'm going to translate this whole thing. Isn't this cool? You can do all this stuff on this geometry sketchpad. We're going to translate this one along the marked vector. So there it is. Now that's pretty cool because look what it does. Now if I take this guy and I slide him around, see it's going to change both of those. And so as they get closer together, all I've really done is just set those up so they're tail to tail.
So you kept going
Right.
around because they like land on top of each other?
They sure could.
Wow. Oh yeah.
Look at that.
Cool.
All kinds of fun, right? So now let's go ahead. So this one up here is the initial velocity. This is the final velocity. So wouldn't you agree then that the change in velocity is just going to be the difference between the final velocity and the initial velocity, right? Let's write that down. So we know that the final velocity minus initial velocity equals change in velocity, right? Agreed? Okay, so then what's that look like? Well, another way of saying that is final velocity equals initial velocity plus change in velocity, right? So isn't the change in velocity vector going to have to be the one that does this, that starts there and ends there, because this is V naught and that's V final, right? So V initial plus delta V has to equal V final, right? Everybody agree? Okay. So let's go ahead and build that vector then. So that's just going to be, we're going to use these two endpoints and we're going to construct that segment. They're just going to be segments for us, but
Isn't that like an isosceles triangle? The exact.
it is an isosceles triangle. You're exactly right.
Wow, I know geometry.
Yes, you do.
Is that what?
Okay. So that's delta V. Let's label this one. Okay, let's call that delta V.
They already have it as. You're in the center.
I know.
Let's call it dV for delta V.
Yes. You got a D in there.
Okay, so what's going to be, let's figure out then what's going to be what's going to be delta r? Isn't delta r just going to be the vector that goes from there to there?
Yeah.
Everybody agree? Okay. So let's look at that one. So
What's the R mean?
position, right? So it's just right the position. There's always going to be a distance r from the center, but at a different angle,
Okay.
pointing a different direction. So think of these as being vectors. Think of it this way. So here's r naught, and here is r. So this must be delta r, right? Okay.
Got it.
So now let's define construct segment. Okay, let's go ahead and label him. And that's dr, right?
Yeah. 2D's in there now. I got one in.
Doctor. Okay. All right, so notice what happens. Okay, let's go ahead and measure this angle. How about? Let's measure angle AST. Oops. AST. So we'll measure that angle. There it is. I'm going to put that one in there so we can see it right next to this guy. And then let's measure this angle. Let's. How about if we label these guys? Show labels. That's good. We leave it like that. Don't want to move them. How come they're primes? Just because they've been moved from over here, right?
Right.
Okay.
What happened if you move the triangle like all the way almost to the top, but it just form a circle?
If I did what?
Never mind, you can't do it. Once we start, don't delete anything after this. I want to see
Okay. You can play with it. So we're going to measure this angle. U prime, A prime, V prime, which is the same as this angle would be over here, right? So if we measure that angle, what do you notice?
It's not. Wait, I can't
It's
see
exactly the same.
It's exactly the same. How about
That
that?
was a trick question.
Okay, yeah, it's exactly the same.
Okay, now can you go all the way up? Yeah. Oh, that's boring. I thought it'd be something cool.
Okay, let's measure these lengths. So we know what the radius is. It's right there, right? Okay, let's measure this length.
It's gonna be the same.
Well, not necessarily the same length.
Why? Oh, wait, no.
Okay.
Why?
Okay, let's put the radius
Why is
down
that
here.
different?
Well, because I can make these, right, I can tweak these. I can make these longer. I could make this,
Oh, I see.
right?
Oh, see, okay.
But they both. Oh, never mind. Yep, I get it.
You get it?
Yeah.
Okay, what did I,
You accidentally messed it up though, right?
no, I don't think so.
That one changing, but the other one isn't
T
changing.
to, what did I measure?
We don't
T
know.
prime,
Look
where's,
how that one's changing. Isn't the one above the right one?
No, because that angle right here is still.
A, oh, okay, so this is, oh, okay, I measured that's the wrong radius. Whoops. Yeah, but remember, that was a radius. I should have hidden that. That's a radius for the little circle we used to construct stuff that then we made disappear. So I'm going to get rid of that. Oh, let's not do that.
Oh, okay.
Yeah.
That was scary. I'm like, oh
Yeah,
my god.
yeah, that would have been bad. Oh,
Oh, maybe don't do that.
maybe. Oh, I can't. I can hide it, but I can't. Yeah,
Oh, that's
270.
there we go. Let's hide it. Okay, so what we really want, I want this measurement. So now let's look at this. So I need this measurement, measure distance, length. So there's R sub 0, right, is 7.290. Okay, that one's going to only change if I change the radius of the circle. Okay, look, everything changes. How about that? Isn't that cool? So then we'll measure this length right here. So this one I want to get rid of, I think. I don't think I need that one for anything. Oh my gosh.
No. I like when you do that. It just gives me a little heart attack every time.
There we go. There we go. Whoops. Okay, so there's a length. That's the length of whatever they called that thing. Okay, that's fine. So this one's going to change. If I tweak the length, that changes, right? Okay, but what I want to do now, let's compare that length to this length down here, to the length of dV.
Is the dV to be shorter? Looks like it. Yeah.
Measure length. It is. It's a little shorter. That's true. Okay, and let's measure this length. So we had that measurement goes with that segment. Now let's measure this.
One of them's going to be the same. That's going to be the same.
Okay, so this guy goes right there.
So
Close.
close.
Okay, but now let's try something else. Can I do calculations on here? I think I can. I can do a calculate, yes. So let's calculate. Oh. So I want to calculate this distance divided by, this is going to be so cool if I can do this distance. And it gives, oh, look at that. That's so cool. It gives me that calculation. Okay, everybody see that?
Yeah, why does that matter?
I did not know that I could do that. That's pretty cool. But now, okay, now let's watch. Let's calculate, do another calculation. Let's calculate
Okay, but those ones are the same.
this distance divided by this distance. And what do you know?
I totally predicted that.
Amazing. Amazing, huh?
Kind of foreshadowing.
And look, they stay the same. No matter what I do, they stay the same. Right? Everybody agree?
Wait, so one line divided.
Okay, why'd you divide those lines?
Yeah.
Okay,
why those ones?
I divided those because we're going to use that fact. But why does that work, really? The reason that works is just because we have similar triangles here, right? We know we have similar triangles because
One of the triangles came from.
these are, Delaney pointed out that these were isosceles triangles, right?
Yeah.
So if they're isosceles triangles, that means that the base angles must always be congruent, correct?
Yeah.
Okay. Well, if we know that the vertex angles, which we already measured, are congruent, then the base angles must also be congruent, right?
What does that mean, congruent?
Congruent means that the angles have the same measures, right? That they're interchangeable.
Oh, yeah. Like
Okay.
45
And wouldn't you agree that if all the angles in a triangle are congruent, then the triangles are similar, right? They could be different side lengths, but the angles all have the same sizes, so they're proportional, in other words.
Yeah.
So you could have, if we had just said that first, you would have made the prediction that these calculations were going to be equal, right? Because they're similar triangles. So if they're similar triangles, the ratios of corresponding sides should be equal, right? Doesn't that make sense?
Yeah.
Right? So in this case, we just did like short, the ratio of short divided by long equals short divided by long for this triangle. Okay? That's useful to us, though, because let's take this ratio. Let's take this ratio of delta R over R, okay, is equal to the ratio of delta V over V. Okay? Everybody agree? Isn't that what those are?
So
Right?
distance and velocity.
Right. And we're going to say here that these are both, this is my initial velocity and that's my final velocity. But what we're going to talk about here, we don't even really have to specify. We're just going to say that those even could be like speeds. Okay? But the magnitude of that side of the triangle is the speed, the magnitude of that side is the speed. They're the same, right? And so dv over v equals dr over r. Same thing here. These are both just the radius, right? We know that's the initial position and that's the final position, but the magnitude of both of those is just r, the radius of the circle, okay? What if I did something really tricky here? What if I said now, can I move this? Oh, I can't. So it's all right. So we've got this equation. We've got the equation delta r over r equals delta, should be a delta v over v. Okay, let's divide each of these fractions or multiply them by 1 over delta t. And delta t is just how long it took to go from there to there, right? Okay. Well, what is delta r over delta t by definition? What's the change in position over change in time?
Velocity.
Velocity, right? So look at that. So what we've got here is, this is the same thing as saying v over r equals, now what is delta v over delta t?
Acceleration.
Acceleration over v. If I solve that for a by multiplying each side through by v, aren't I going to get the equation a equals v squared over r? Okay, that is my equation for centripetal acceleration. That's our way we can calculate it. Okay,
That's like the actual equation?
that's the actual equation, yeah. So, and that's kind of cool that we proved it, that's geometrically, it's kind of cool. I thought it's kind of fun to see a different way to prove something. So, that tells us that if we have an object in uniform circular motion, let's define what that is. Uniform circular motion then just means an object that is moving in a circle at constant speed, that's it, right? All we have to do to find out the centripetal acceleration, we just take the square of the speed divided by the radius of the circle it's moving in, and that gives us centripetal acceleration. How about that? Okay. We could do one other thing that's kind of cool here. What if we were to take, I just want to show you one little thing before we get rid of this stuff. Let's take this vector, and I'm going to, so delta v was our change in velocity, right? Over this period of time though, right? So where was our average position during this time? If we started here and we ended there, where's our average position?
In the middle.
In the middle, right? Does that make sense? Okay, so the average position would be the midpoint of this segment, right? Okay. Okay, so let's construct, oh, it's not letting me do midpoint. Because I probably have to do,
It's just basically what you just did.
Probably do the 2 dots.
there we go.
Oh.
Okay, so there it is. So there's my average position. Let's define this vector. Oops. In what direction is that change of velocity? So that's our change in velocity acting at our average position. In what position is that change in velocity acting? Where is it pointing?
Right.
Right towards the center of the circle. What did we say centripetal meant?
Center seat.
Center seeking, right? And so if we were to kind of calculusify this, all we would really have to do is just move this interval back so delta t was very small. But look at the direction that it's always pointing. Towards the center. How about that? See what I'm saying?
Can you make it lower? Let's go all the way around. So
I could, if I go clear down.
Right, just
Right. Now that's kind of weird if I go over there, but now we're thinking about an average, right? So our average position actually ended up being here, right?
Well, why doesn't it point toward the center?
Well, it does. It does point towards the center because really we were never actually there, right? We were really, like, we traveled along this path, but at the halfway point right here, that's where the centripetal acceleration would be pointing, right?
Okay.
Does that make sense?
Yeah.
Whoops.
Cool.
So my point then is just undo. Now I should be able to scoot them back. That's kind of cool, though, isn't it?
It is.
Right? So it's a center-seeking vector, and the magnitude of the centripetal acceleration is given by this equation. Okay? So then let's just try just a quick example of a little problem we could do then. If we wanted to know, for example, let's say I have a 1.3 kilogram rock attached to a string.
Do we have problems like this on physical science?
Yeah.
Did the other class learn this?
No, they haven't learned this yet.
Okay.
Attached to a string, and let's say it's moving in uniform circular motion at, let's say it's moving at a speed of v equals 2.0 meters per second, and the radius of the circle is 1.2 meters. Okay, what's going to be the tension in the string? We can figure it out.
Yeah.
Right? Because really all this is uniform circular motion, right? There's r, there's my speed, right? And so we know that centripetal acceleration is just v squared over r. So that's going to give me 2.0 meters per second quantity squared over 1.2 meters. So that's 4 divided by 1.2 is what? .3 repeating. So 3.3 repeating, and then what are the units going to be? Meters squared per second squared divided by meters. So one of the meters cancels. Yeah, how about that? So my centripetal acceleration is 3.3 meters per second squared. If we want to know what the tension in the line is, well, the centripetal force is just the mass times the centripetal acceleration, right? Everybody agree? What's the only force acting on this object? Centripetal acceleration. Okay. So that's the net force, right? And so that's just equal to then 1.3 kilograms times 3.3 meters per second squared, which is 4.3 repeating. And so to our, like the 2 sig figs, we'd get 4.3 newtons as the tension in the string that keeps that rock moving in a circle, right? How about that? Okay. So this could be useful. Like if you wanted to know, for example, if we knew what the coefficient, the rolling coefficient, so it's really a static coefficient of rubber on asphalt is, and you knew what the radius of a turn was on a racetrack, you could determine, so that would allow you to calculate what's the maximum, if you knew the weight of the car, right? And you knew, does that make sense? So you knew the normal force. You could calculate what the maximum centripetal force that friction could provide for your car is, right?
Which means what?
Which means, so if you're going around it, why would your car start skidding if you went around a corner? It would start skidding because the tires couldn't provide enough centripetal force to turn you in a circle. See what I'm saying? So that way you could calculate what your maximum speed on that curve would be, right? Does that make sense? Because you would know, okay, this is the maximum amount of centripetal force that that the tires could provide. And so what kind of centripetal acceleration does that amount to? Just divide the force by the mass of the car. And then you would know this, right? You know the radius of the turn. So you would know that centripetal acceleration equals v squared over r. So if we solve that for v, doesn't that just mean that v is the square root of centripetal acceleration times radius? So that's something that we could calculate, right? Because we knew what the friction was, right? We can measure the radius of the racetrack. So this tells us what the maximum speed would be that we could travel at without skidding off the turn.
We should really enter a race. We
Think
know
so?
how to melt our tires.
Yeah, that's right. You guys
And
learn
how
all
to
kinds
go
of
around
fun
the-
stuff. Yeah, yeah.
You would just win the drag car race.
That's right. We just use physics, right?
Yeah.
Okay, so you got it.
Yeah.
That's it.
Ooh.
You know all about centripetal acceleration and force now.